In this video, we're going to discuss another way of doing shortest distance, which I prefer, and this method will allow us to find the point at the minimum distance as well. So this is the question we have done before. So we had a point in 3 dimensions to a line in 3 dimensions. This time we're going to utilize the parameter, this parameter t right there. Quick reminder, before what we have done for a point in 3 dimensions to a line, we had to use area of parallelogram, but this did not work for other scenarios. In the scenario where we had 2-dimensional line or a plane, we had to use a different formula. So this method I'm going to talk about right now we'll be able to use it no matter what we have, a line in 3D or 2D or a plane. Okay, so let's proceed to discuss this. So what we were going to set up first of all is we're going to create the point, even though we don't know what it is, we're going to say let R be the point on the line that is at shortest distance to point Q. Because this point is on the line, then this equation of the line is going to create, we can use this equation of a line to create an expression for this point for some unknown t. So the vector OR, okay, so this is a position vector that is, its tail is at the origin, that's pointing at the point R. The way I created this component form is I've taken 0 plus 1 times t as the first component, then the y component would be 1 plus 1 times t, and so on. So after you've created an expression for the position vector OR, which is actually going to look very similar in its notation to the point itself R, then what you want to do is find the vector QR. Even though we don't know what that t is, we'll just find an expression again for this vector QR. In order to find QR, what we're going to do is utilize the known point Q, but we'll just convert it to position vector OQ. And then the OR expression that we found here will be used here too. Oops, I forgot a vector symbol here, pretend it's there. So once you have this created, what you want to do now is look at this statement that we had before. We've learned that if we have two vectors that are perpendicular to each other, then the dot product between them is going to be 0. This expression is going to allow us to find the actual value of t, because this gives us an equation with only one unknown t. Solving for that, we get the value of t to be -1/3. So the shortest distance for us is going to be just the magnitude of this vector QR. That's pretty obvious because that's going to be at 90 degrees, and now that we have the t value, all we have to do is put it into this QR, which I've done here, and then these lines here, they mean to find just the magnitude of this vector on the inside. And when we do that, we would find the answer to be 1.8 units, which is the same answer that we had before when we utilized a different method. The one that we used before was the area of parallelogram method. So the reason why I like this method better is because if there is another question that asks to find the point at shortest distance, so then this is going to be very easy to do because all you have to do is plug in this -1/3 value of t into the position vector OR, and that will give us the point R. You do have to restate this. Just because you found the vector, you cannot just say this is equal to point R, because a vector and a point are not equal to each other. The notation looks the same, but they are not equal to each other. So please restate it at the end. Now, this is not the only way to find the point R. That's my favorite way, but there is another way, and the reason why I show you one more method is because when you have questions that are more rich type questions, kind of like tips, thinking, inquiry, and problem solving, you do want to have as many tools in your belt as possible to find a solution. So I'm going to show you how to find this point R, so pretend we never found it, using a projection instead. So what we're going to do is, because we're looking for point R, the position vector OR will have identical notation to it. So let's start there. But what we're going to do now, we're going to split this up into two other vectors using the point P, because that's something that we do know. So OP plus PR is going to give us the vector OR. Now, this side OP is fine because we know what that is, but PR is this green vector right here. We don't know what that vector is because we only know one of the endpoints of this vector. We don't know R. So we're going to use the vector P to Q to help us, because we know both P and Q. We can utilize that in the following way. So I'm going to show you that PR is actually the same thing as a vector projection of PQ onto M. The M being here the direction vector, which I drew over here, this red line right here with an arrowhead on this line itself. So if you recall from this unit, or actually from the last unit, is that when we have a projection of a vector onto another, we think of the second vector M here as being the floor, and we're going to think of the shadow of the purple vector on this floor, which gives us this green line. The reason why the arrow is in this way, because it's in the same direction as the vector PQ that is being pulled in the forward direction. Then this is a reminder of the vector projection formula. So this is not the same thing as scalar projection, slightly different, so be careful. And we will know almost everything about this formula. We know the M, but we don't know PQ. We do know the point P and point Q, so that's easy to be found. And that's what is done on the side over here. So you can pause and take a look at that more closely. And once you have PQ, we just put it all into this equation. We do the dot product on the top. On the bottom, we have magnitude, and then we have a square on it. So the square and square root will cancel each other out. So it's going to simplify to just 6 on the bottom. And this fraction becomes just -1/3. Then when you distribute that fraction into the vector and add all the components together, you would get the same result that we had before, as you can see there. Now I'm going to utilize again this method using parameters, but this time I'll show you how it works in 3 dimensions. This time we have a parameter K and a parameter R that we'll be using, so it's going to be a little bit more complicated, but it's the same strategy. So first of all, define a point on the plane at shortest distance. I call it point Q. Since this point Q is on the plane, then we can represent this point Q, or vector OQ, position vector, using the parameters from the equation provided for the plane. We just don't know what this K and R are. So all we have to do is find those two parameters. So first of all, we're going to find vector QR by going through the origin. So even though we don't know what the parameters are, we can find an expression for the vector QR. The reason why we want to do that is because we know the following. QR is at 90 degrees to the plane. That means it's at 90 degrees to the 2 direction vectors which are going to be lying on the plane. This in turn implies that the dot products are going to be equal to 0, and this will allow us to find the missing K and R parameters. So this green one, I have over here my calculations. Feel free to pause and take a look in detail. And then this purple version, I have over here my calculations. And then you had to solve these two equations, two unknowns. I do not show the steps here because I ran out of room, but these are the solutions. Feel free to actually solve it and see that these are correct. And as soon as you know your parameter values, then the shortest distance is going to be the magnitude of this vector QR. And then if I asked you to find the actual point Q itself at shortest distance, all you had to do is stick the values of the parameters into this expression over here, and you'd have both the shortest distance as well as the actual point at shortest distance, which is written over here. Here's a solution for you to verify when you try it.